The reason why we have to context switch among threads is because the CPU has one set of registers to describe the active execution context, the thread that's currently running on the CPU. These include the stack pointer and program counter in particular. Over time, however, hardware architects have recognized that they can do certain things to help hide some of the overheads associated with context switching. One way this has been achieved is to have CPUs that have multiple sets of registers, that each set of register can describe the context of a separate thread, of a separate execution entity. One term that's used to refer to this is hyperthreading. So hyperthreading refers to multiple hardware-supported execution contexts, hyperthreads. There's still just one CPU, so on the CPU, only one of these threads can execute at a particular moment of time. However, the context switching between these threads is very fast. And just basically, the CPU needs to switch from using this set of registers to another set of registers. Nothing has to be saved or restored. This mechanism is really referred to by multiple names. So in addition to hyperthreading, a common term is also to refer to this as hardware multithreading or chip multithreading or simultaneous multithreading, SMTs. So we will use basically these two terms, hyperthreading and SMTs, more dominantly than the others. Hardware today frequently supports 2 hardware threads. However, there are multiple higher-end server designs that support up to 8 hardware threads. And one of the features of today's hardware is that you can enable or disable this hardware multithreading at boot time, given that there are some trade-offs associated with this, as always. If it is enabled, as far as the operating system is concerned, each of these hardware contexts appears to the operating system scheduler as a separate context, a separate virtual CPU onto which it can schedule threads, given that it can load the registers with the thread context concurrently. So for instance, in this figure, the scheduler will think that it has 2 CPUs and it will load these registers with the context of these 2 threads. So one of the decisions that the scheduler will need to make is which 2 threads to schedule at the same time to run on these hardware contexts. To answer that question, let's remind ourselves of what we talked about when we talked about the context switching time. We said that if the time that a thread is idling, that a thread has to wait on something to happen, is greater than twice the time to perform a context switch, then it makes sense to actually do the context switch in order to hide this waiting, this idling latency. In SMT systems, the time to perform a context switch among the 2 hardware threads is on the order of cycles. And the time to perform a memory access operation, a memory load, remains on the order of hundreds of cycles, so it's much greater. So given this, then it means that it does make sense to context switch to the other hardware thread. And in that way, this technology, hyperthreading, will help us even hide the memory access latency that threads are experiencing. Hyperthreading does have implication on scheduling in that it raises some other requirements when we're trying to decide what kinds of threads should we co-schedule on the hardware threads on a CPU. We will discuss this question in the context of the paper Chip Multithreaded Processors Need a New Operating System Scheduler by Sasha Fedorova and others.